Next, we're going to look at the one sample t-interval, or simply t-interval as most people call it. The purpose is to estimate a population mean mu, conditions, SRS, and normal population. Again, the third condition, that the population must be at least 10 times the sample size, is normally not checked because it's obviously met. But again, you should always think about whether or not your sample observations are truly independent. The formula is x bar plus or minus t star times s over the square root of n. So like all confidence intervals, this has the general form statistic plus or minus critical value times standard error of the statistic. On the calculator, you can find this at stat tests 8 t-interval. Let's revisit the example about Jimbo. He loves this kind of candy bar. He suspects that they don't really weigh 1 ounce as stated on the package. These are the weights that he got from 10 randomly selected bars. We're going to construct a 90% confidence interval for the mean weight of this kind of 1 ounce candy bar. Now we're going to define our parameter of interest. Mu is the mean weight of this kind of 1 ounce candy bar. Checking the conditions, SRS, again, we don't have an SRS most likely, but we have a random sample and that should be representative. The normal population, again, we're not told we have a normal population. We can't fall back on our first line of defense, which is the central limit theorem, because the sample size is too small. We would need 30 or 40 observations to invoke the central limit theorem here. So our second fallback position is looking at the data. Here are the weights. Again, here's a stem plot. You could also do a normal probability plot or a modified box plot. What you want to see is symmetric data, single peaked, and free of outliers. And that fits the bill right here. So these data could have come from a normal population. And the 90% confidence interval for the mean, mu, is x bar plus or minus t star times s over the square root of n. We plug in 0.985 for the mean and 0.022 for s, and the sample size is 10. Where does this critical value come from? Well, that critical value comes from a t-table. Okay, here is a table of t-distribution critical values. And what you do when you look at this table is you start on the left and you look at the degrees of freedom and you find the row that has the degrees of freedom that apply to your particular case. Down here on the bottom are confidence levels. If you're making 90% confidence interval, you want to be in this column. So you go up that column until you're in the row for 9 degrees of freedom, and the entry where that row and column intersect is the critical value that you want. So it's 1.833 in this case. So that's where that number came from. And then we simplify everything. We get 0.985 plus or minus 0.0126. That's our margin of error. And then the interval is 0.9724, excuse me, and 0.9976. Then as the conclusion goes, we'd say I am 90% confident that the true mean weight of this kind of 1 ounce candy bar is contained in the interval from 0.9724 to 0.9976. Now you might notice that 0 is not in this interval. So you could use this interval to test the null hypothesis against a one-sided alternative where the alpha level that you're using is 5% or 0.05. An alpha level of 0.05 and a one-sided test, one-sided alternative, corresponds to 90% confidence in this interval. So because 0 is not in this interval, we could reject the null hypothesis that the true mean weight of these candy bars is 1 ounce in favor of the alternative, that it's less than that. So you can use these confidence intervals just like you did with the 1 proportion or 2 proportion z intervals when we were looking at proportions. You can use them as ways of doing tests of significance too.